Good morning one and all. Welcome to session number 18. This is Mounika working as an assistant professor in KL University, Vijayawada. In today's session, we are going to discuss about single source shortest path method in design and analysis of algorithm. So before going to discuss about single source shortest path method, I just want to mention about shortest path method. So shortest path is nothing but shortcut way between two nodes or two cities. So to know this shortest path, we are having some algorithm. So these algorithms are used to calculate the minimum traveling cost from source node to destination node of a graph in optimal time and space complexity. For example, I am considering two cities, those are A and B, and I am giving a direct way from A to B is 9 kilometers, and another way is also I am considering, that is A to C and C to B. This is, for example, it is 2 and it is 5. So what we are saying, it is calculating the minimum traveling cost from source node to destination node, right? So my source node is A and destination node is B, right? So what is the distance between A to B is 9 kilometers, and by using C, the distance between A to B is 7 kilometers. So what is the minimum traveling cost and what is the minimum path? It is A to C to B, right? So this is nothing but shortest path. So to know this, we are having several types of algorithm. So generally there are various types of graphs are available, like weighted graphs, unweighted graphs, negative graphs, positive graphs, cyclic, acyclic, and also directed and undirected graphs, right? So if it is having only a single algorithm that handles all the time efficiently is not possible. For that purpose, in order to tackle these different problems, shortest path algorithms can be categorized into two categories. Those are single source shortest path algorithms and all pair shortest path algorithm. Single source shortest path algorithm. In this algorithm, the shortest path of all the nodes in the graph is determined with respect to a single node. That is, only one source node is available. So within that only all the nodes distance will be calculated. So all these are algorithms of single source shortest path, and those are depth first search, breadth first search, multi-source BFS algorithm, disk-trace algorithm, Bellman-Ford algorithm, topological sort, and A-star search algorithm. And all pair shortest path algorithm is nothing but it is just contrast to the single source shortest path. So there only one source node is available, and here this algorithm, the shortest path between every possible pair of nodes is determined. For example, I am giving node 1 and 2, 3. So from 1 and 2, so here 1 is my source node. So in single source shortest path, so from this only all the time the distance will be calculated to every node. But in all pair shortest path algorithm, I will calculate the distance between 1 and 2 and 1 and 3, and if it is available 2 to 3, and this is also we will calculate. So likewise, okay. Then disk-trace algorithm. Before knowing this disk-trace algorithm, some basic points are we need to know. Those are, generally graph is nothing but it is a set of vertices and edges, right? So these graphs are used to represent the distances between two cities. To find the shortest distance from one city to another city, this shortest path algorithm is used. Then this problem is used to find the shortest path from given source vertex to all remaining vertices in the given graph. So that is what we discussed here in this diagram. And before doing that, we need to remember one point is all the distances are positive only all the time, and starting vertex is called source vertex and last vertex is called destination vertex. Then the algorithm for finding this single source shortest path is disk-trace algorithm. So in our session we are using the disk-trace algorithm, which uses greedy method. Greedy strategy is nothing but to generate the shortest path from source vertex to all other remaining vertices. The length of the shortest path is nothing but sum of the weights of edges on the path. So if we want to find out the length of the shortest path, how can we will find? It is the sum of the weights of the edges on that path. For example, I am taking node 1 and node 2 and 3. These are the 3 nodes or 3 vertices I am taking. So 1 to 2 it is already path is there, I am taking as 1, okay, and 1 to 3 no direct path is available. So here I am giving the cost between 2 to 3 is 2, right. So within that we don't know the direct path, so that's why by using these two, the weights of the edges on that path we need to add. So 1 plus 2 equal to 3. So the distance from 1 to 3 is 3, okay. Then coming to the algorithm, so these are the main steps we need to follow. What are those? Disk-trace algorithm assumes that cost of E greater than or equal to 0 for each E in the graph. So nothing but all the time the cost should be greater than or equal to 0 and also positive. Next, the second one is we have to maintain a set of vertices whose shortest path from V is nothing but source node has been determined. So from source node only we need to find out the shortest path to all the vertices, and those should be in the set, right. If it is not in the set, then we have to give that as infinity for the cost or distance, and also we will apply the relaxation property. So relaxation property formula here we can see, and we will explain that in the next slide. And coming to the next one is we have to repeat these two steps until the visiting of all the vertices, okay. So what are the steps we need to follow? First, it should be the cost is positive and greater than or equal to 0, and we have to maintain one set of shortest path vertices, and next one is we have to find out the minimum of all those vertices, and then if it is not in the shortest path vertices, then we have to give the relaxation we have to follow the relaxation property. Due to that we can find out the distance of the vertex until this process is repeated until the number of all the vertices should be visited. So coming to the relaxation property, I am considering 3 vertices 1, 2 and 3. So 1 is my source vertex and 3 is my destination vertex. So I am giving its name is V, and 2 is my intermediate vertex and I am giving its name is U, and these are the distances between 1 to 2 is 2 and 2 to 3 is 4, right. So distance of U is nothing but cost of 1, 2. What is the cost? It is 2, right. So distance of V, it is not a direct path, right. So that's why it is infinity. So initially we will take it as infinity because it is not available, right. So from source node it is 0 and whatever we don't know it should be infinity. And relaxation property, what is the formula? Distance of U plus cost of U comma V less than distance of V. If distance of U is nothing but cost of 1, 2, right. So distance of 2 is 2 and cost of U comma V is 2, 3, right. 2, 3 is less than distance of 3. What is the distance of 3? It is infinity, right. So 2 plus 4 equal to 6. So 6 is less than infinity. So the formula is correct, right. It is true. That at that time we have to use this formula to calculate the distance of that particular vertex, right. So, distance of 3 by using this formula equal to distance of 2 plus cost of 2 comma 3 equal to distance of 2 is 2, right. Then cost of 2 comma 3 is 4, right. So, 2 plus 4 equal to 6 and distance of 3 equal to 6, right. So, we found the distance of 3. So, this is the relaxation property. Then let us check one simple example, due to that we will understand very clearly. And this is the example. I am considering 6 vertices with everyone having relations and everyone having the cost, right. So, what is the first step? We have to select one source node, right. So, I am considering this one is my source node, okay. Then it should be we have to maintain one set, right. So, S equal to, and what is the source node I am taking now? 1. So, 1 will be added into the set, right. So, I am from this only I am going to calculate the distance for all the vertices, right. So, distance of 2 equal to C of 1 comma 2, right. So, this is 2 and distance of 3 it is not available directly. So, that is why I am giving it as infinity. Distance of 4 is 6, right. Then distance of 5 is 20 and distance of 6 is 10. Then what we need to do? We have to find out the which one is minimum one, right. So, the minimum one is 2, right. So, we have to add this second vertex into the set, right. So, I am adding it into the set. So, now my set is updated with 1 comma 2. Then in the step 2 we have to find the adjacent vertex for 2. So, what is the adjacent vertex? It is having only 3, right. So, we have to apply the relaxation property on the vertex 3. So, what is the relaxation property? Distance of 3 equal to, I am doing this via 2, right. So, 2 is my intermediate vertex and 3 is my destination vertex, right. So, minimum of distance of v comma distance of u plus cost of u comma v. So, we have to find out the minimum length between these two, right. So, where u is my intermediate vertex, v is destination vertex. So, minimum of what is v? V is nothing but 3, v is nothing but 3 and u is nothing but 2. It is u and it is v, right. So, we are substituting that values and the distance of 3 comma distance of 2 plus cost of 2 comma 3. Then distance of 3 previously what is the value it is having? Infinity. So, infinity comma distance of 2 is 2 and cost of 2 comma 3 is 10, right. So, what is the after calculating which one is minimum? 12 is the minimum, right. So, the distance of 3 is updated with 12 and distance of 4 is we already having that. So, 6 and distance of 5 is 20, distance of 6 is 10. So, among all these which one is minimum? Then 6 is the minimum, right. So, among all minimum length is 6. So, select vertex 4 as the next current vertex and it should be added into the set of the shortest path vertices, right. So, now current vertex 4, the adjacent vertex for 4 are 2 vertices are available, right. Those are 3 and 5, right. So, we have to apply this relaxation property on these 2 vertices. Those are distance of 3 equal to 1 to 3 via 4 and 1 to 5 via 4 we need to calculate. So, after calculating this we are getting the value as 10 and distance of 5 we are getting the value as 18. So, then distance of 6 is 10. So which one is minimum value? Actually distance of 3 and distance of 6 both are similar values, same values, right. So in this I am considering distance of 3 is my minimum value. That's why 3 will be added into the set. Now my set is updated with 3. So then 3, what is the adjacent vertices are available for 3? There are 2 vertices, 4 and 5, but 4 is already in the list, right. So that's why 4 will not be considered. Then 5 is only available, right. So distance of 5 is equal to via 1 to 5 via 3 is, we are applying the relaxation property, then we will get the value as 12, because minimum between 18 and 12 is minimum of between 18 and 12, it is 12, right. So the distance of 5 is updated with 12. Then distance of 6 is already there, that's why I am taking the same thing, and among these two values 6 is the minimum value, right. Among distance and we have to choose the next current vertex and we have to add into the set, right. So I am adding into the set and I am going for the next node, that is for 6 it is 5 only, right. So we have to relax this vertex 5 via 6 and I am applying the relaxation property formula, and here we can observe one thing, that is here minimum value, minimum distance of 5 is 18, but previously we observed 12 is there distance of 5. Then what should we do? Why we considered 18? Because in the path is generally one way is 1, 4 and 5. So this is one path, right, and it is having 6 and 12. Another path is 1, 2, 3 and 5. This is the another value, but here we can observe one thing, that is in the relational property one intermediate node is there all the time, but here in this path 2 intermediate nodes are available. So this will not consider. So this is the only path we will consider. So what is the minimum value here? 18. So that's why we are taking the 18 is the distance of 5. Okay. Then we are calculating the minimum value between 18 and 19, then 18 is the minimum value. So distance of 5 is 18 and we will add into the set of the shortest path. Okay. Then we can observe all the vertices are visited, right. So that's why I am giving the I am giving the path between all the vertices. Okay. Okay. So in step 6 we can write clearly as 1 to 2 is 2, we already know, and 1 to 3 is, we can observe that 1 to 3 it is having 1 to 3 directly it is infinity, and another path is 1 to 2, 2 to 3, that is 12, and another path is 1 to 4, that 1 and 2 to 3 is 10. So in this which one is minimum? This is the minimum. So that's why we are taking the minimum one. Then 1 to 4 is already available, and 1 to 5 also we will check. 1 to 5 directly it is there and it is 20, and by using via 5 it is 18, and via 6 it is like this, and this is the path for 5. So within this is already cancelled, and these both are similar, so that's why I am considering this path, okay, and this is also not considering because it is not a minimum value. So finally this is the path for the 1 to 5, then 1 to 6 is 10, right. So this is the example for disk-cross algorithm. So let us discuss about algorithm for disk-cross algorithm. Algorithm shortest path is we are writing an algorithm regarding shortest path, and we are taking the source node as V, and cost is the distance between them, and distance is the distance which one is array, and n is the numbers of vertices available, okay. Then the algorithm purpose is to calculate the shortest path between the all the nodes, right. From vertex V to vertex J in a graph with n vertices, distance of V is set to 0. So we already discussed from starting we will set it as 0. Then G is represented by its cost adjacency matrix. Cost should be 1 to n and 1 to n, right. Then I am opening the loop, and it should I am calculating for 1 to n vertices. Then S of I equal to false, distance of I equal to cost of V comma I. It means it sets S of V to for each vertex I, the array S is initialized, and it should be false, okay. Then the distance should be cost of V comma I, and S of V equal to true, then distance of V equal to 0. Then after going into the second vertex, so for num equal to 2 to n, so we are visiting 2 to n vertices, then it should be we have to choose U from among those vertices not in S. U is nothing but intermediate vertex, and such that distance of U is minimum, it should be minimum. Then if it is true, S of U equal to true, then we are applying the relaxation property, okay. So this is the disk-cross algorithm. So before that, so what are the things we are doing here is, first it should be either positive or not, we need to check, and it should be greater than or equal to 0, and second one is we have to maintain one set for the shortest path vertices, and third one is we have to check whether it is what is the minimum value, and if it is not available for the path, and we will apply the relaxation property. Relaxation property formula is if distance of W greater than or equal to distance of U plus cost of U comma W, then distance of W is equal to distance of U plus cost of U comma W. Then this step will be repeated until the all the vertices should be visit. And time complexity of disk-cross algorithm, in the loop, for loop of line 6 takes, it is this one takes the big O of n, and for another one for initialization purpose it is taking big O of n, and from lines 11 to 21 it is for main loop, and there it is taking big O of n square. So each execution of this loop requires big O of n time at lines 14 and 17. So the total time of this loop is big O of n square, right. So the total time taken by this algorithm is big O of n plus big O of n square equal to big O of n square. And coming to the applications of single source shortest path algorithm, these are mainly using in mapping softwares like Google or Apple Maps, and also road network operations and logistic research, and also this is very useful in computer networks like the internet, etc. And this is one more example for practicing. So please do practice, and these are the sample questions about our session. Thank you.